This video is on banked turns. A car of mass m goes in a horizontal circle on a banked curve of slope theta. So you can see the slope here in the picture, and the car has a mass of m. At each instant shown, the car is moving toward us. You can see the headlights there. The coefficient of static friction is mu sub s, and the circle's center is a distance r away. Somewhere over here off the right side of the screen, that's where the center of the circle is, based on the way this thing is a banked curve. How is the car moving in each picture? This one in the middle is moving at the perfect speed. You can tell by the tires. This one, it's coming towards us, and it looks like the car is tending to slide down the ramp, which means it's going too slowly. And on the right side here, it looks like the car is trying to jump off the ramp. See, it's trying to skid off the ramp. I think we're going too fast. So what's happening with friction? Inside each banked curve, write either Fs equals 0 or draw and label an arrow showing the friction force. In here, Fs is equal to 0, no friction there. And here, which way are things happening? See, the car is trying to slide down, and friction is trying to hold it back. So Fs is going to be going that way. And here, we talked about the car going too fast. It's trying to slide off the ramp, and friction is trying to help us keep it on there. Just like that. We now consider the case of the car moving at a perfect speed. Draw a free body diagram on the dot shown and don't show components. If we're moving at a perfect speed, there's no friction. So what would our free body diagram look like? I put the banked curve in there to just kind of help us focus. mg is going to act that way. And then what do we have here? We have normal force, which is at right angles to the surface, Fn. And isn't it true that right in there, that is theta as well, that little angle right there. So let's sketch a coordinate axis that applies to this case. All right, now this is very, very important. And the reason it's important is because one of the axes must always point in the direction of an acceleration. And in what direction is this car accelerating? Isn't it true that this car is accelerating that way? I'm going to call that the x direction. And then the other axis then has to be at 90 degrees to it, so that's the y-axis. And the reason this is strange is because up until now, whenever we've had a situation like this, it is mg that has gotten resolved into its components. Mg cosine theta, mg sine theta. But what's going to happen here is, because the car's acceleration is straight horizontal, that has to be one of the directions that we deal with. So what's going to be resolved into components is now the normal force. And if I were to draw a little dotted line there, isn't it true that there's theta right there as well? So here, look at my coordinate axes. mg, we're not going to resolve it into its components. It's Fn that has to be resolved. So now let's just do Newton's second law and see what falls out. How about we sum the forces in the y direction? In the upward direction, it would be Fn cosine theta minus mg, and that should equal the mass of this car times the acceleration in the y direction. Now, in the y direction, it's not accelerating. It's not accelerating up, it's not accelerating down. So that means that this term turns into 0, which means that the normal force is equal to, put the mg on the other side, divide by cosine. Wouldn't it be mg divided by the cosine of theta? Now, what we want an expression for the speed of the car. So let's see if we can get that. by writing the other Newton's second law equation, which is the sum of the forces in the x direction. The direction that it's accelerating, I always choose that to be positive. So to the right is going to be positive. So that's going to be Fn times the sine of theta. Hey, you know what? No other forces in the x direction. That's it. So that is the net force in the x direction. And that needs to equal the mass times the acceleration in the x direction. The acceleration in the x direction is the centripetal acceleration, which is v squared divided by r. We're asked to find v. V is what we're looking for. So in other words, we have to be given everything else in this expression to make it work. We're looking for v. We know what r is. We know what m is. We know what theta is. Uh-oh, we're not given Fn. Look at that. Our first Newton's second law equation to the rescue right in there. Let's put that in there and see what we get. mg over cosine theta times sine theta equals mv squared over r. Can we simplify this? I think the mass is going to cancel. It doesn't matter if this is a car or a truck or a motorcycle. As long as we have that banked curve, the speed is going to not be a function of the mass. So we're going to put r over there. I'm seeing gr. What does that simplify to? Tangent? Somebody better check that. gr tangent theta. G times r times the tangent of theta square rooted. That's what you get when you got no friction. That's the ideal speed to go around a banked curve. If you don't want friction, that's the speed you got to go at. It matters how much the bank is, and it matters what the radius of curvature is, but it doesn't matter what the mass is.